So in today's lesson, we're going to be learning about acids, bases, and the pH scale. So you may not know what bases and the pH scale are, but we're going to talk about them today. We're going to start with something a little bit more familiar to you, and that is acids. So most of you can think of acids because you've encountered them in your everyday life. So some examples of some acids you may be familiar with are, any kind of citrus fruit. In this case, I've included the lemon because it seems to me the most sour. Vinegar is definitely an acid. If you eat food with lots of vinegar, like a salad dressing, then you definitely can feel a little bit of heartburn, and that's just the acid going to work. And some pop. And so I'm going to see what I can do about getting a can of pop. We'll do a little experiment, put a nail into a can of pop and see what happens to it after a day or so. And the reason that we should expect to see something is because it turns out that acids should be able to react with metals. So if in fact Coca-Cola or Sprite or Pepsi are indeed acids, then they should be able to react with a metal such as an iron nail. But what they all have in common is that sour taste and that they will react with metals. So most of us, when we think of acids, we think of a compound that is corrosive or that can break down other materials. So what is it from the chemical perspective about acids that allows them to do the damage that they do? Well, as it turns out, an acid, by definition, is a compound that when it dissolves in water will release hydrogen ions into solution. And so it's in fact these hydrogen ions that are floating around in solution that are causing the corrosion, that are causing the damage that we're seeing. So for example, I've used here an example that I think is fairly common. If somebody were to ask you to name an acid, many of you might list hydrochloric acid. So hydrochloric acid will have the formula HCl. It's quite a simple acid, but when we take it and we make it into an aqueous solution, when we dissolve it in water, then it ionizes, it dissociates into hydrogen ions and the chloride ions. Now the chloride ions really don't do a whole lot, but it's these H+ ions, the hydrogen ions, that are going around and doing a whole lot of damage. Alright, so now let's move on to bases. It's the second topic in today's lesson. So bases, which you may or may not be familiar with, less people seem to be familiar with them, they are what we call the chemical opposites of acids. So sometimes instead of calling something a base, it's important that we might call something alkaline, sort of like we might call a substance acidic. We usually don't call a substance basic. We would say it is alkaline, but sometimes we'll still see the basic. So I just wanted you to know that term, alkaline. Now, it's interesting. An acid, if you're to feel an acid in your hand, it just feels like regular water, and after a while it will probably burn you if it's strong enough. But I can often tell that, I might have some base on my hands because when I rub my fingers together, it feels a little bit slippery. And so think of like soap, right? And in fact, many soaps, many cleaning agents are in fact alkaline. They are bases. Now most of us don't taste soap, except maybe if we say some bad words when we're a little kid and our mother washes our mouth out with soap. But bases will typically have a bitter taste. So I like to think about baking soda. If you've ever just tried baking soda on its own, obviously we wouldn't be tasting Windex or Drano. But if you taste baking soda, you can see it's a little bit bitter. I tend to think about, and I'm not sure actually if a Tylenol tablet is in fact bitter, or a base rather, but I know certainly that it's bitter. So that's what I think about when I think of bitter, sort of if I were to crunch a Tylenol in my mouth, that feeling that I would get. Now, interestingly enough, one point of difference between acids and bases is that an acid will react with metals, like the iron nail that I mentioned, but bases will not. And that's part of the reason that we use Drano, which is a very, very strong base, to unclog drains. If your drain is made of metal, then you want to be able to unclog the big chunk of hair or whatever it is that's blocking your drain. You want to basically break that down, but you don't want to break down, your pipe along with it. And if you were to use a strong acid, then your pipe would be corroded, and that would do more damage than you intended. So Drano is a very strong base, which is corrosive and will break down the hair or the materials that are clogging your drain, but will not break down the pipe itself. And for that reason, it's designed to do that job. Another substance that is fairly strong base that you might be familiar with is Windex, and so Windex has what we call ammonia in it. And so if you know that characteristic smell of Windex, then you know what ammonia is. And so all three of these substances are fairly commonly known bases, and we'll explore some other ones in class when we do a lab experiment in the near future. But notice that all of these to some degree are cleaning agents, and in fact many cleaning agents will be basic or alkaline. But what is it about a base that, like Drano for instance, that makes it able to break down our big hair chunks? The acid produces hydrogen ions that do damage. A base dissolves in water to produce hydroxide ions. And so those hydroxide ions are what are doing the damage, or what are doing the corroding. So for instance, if I were to take a compound like sodium hydroxide, and you can see that it contains the hydroxide polyatomic ion. And it's also ionic, and so many ionic compounds in water will break down and dissociate into their ions. And the sodium ion will just kind of be hanging around there, but the hydroxide ion is when freed up is going to be able to go ahead and break down many other compounds and acting as a base. So there are things that allow us to test how acidic or basic a material is, or a solution is, and those are called acid-base indicators. And we're going to talk a little bit about this. Perhaps some of you that have hot tubs or that have a swimming pool may use some sort of an acid-base indicator in order to indicate how acidic or alkaline a solution is. And so I'm going to go through a couple of them, and then hopefully when we meet again in class I'll do some demonstrations to make this a little bit more clear to you. So the first one is litmus paper. And so litmus paper are just these little pieces of paper, and they come in blue and they come in red colors. They're just slightly different from a chemical standpoint, so that they come out at different colors. And so if you were to put a piece of litmus paper, whether it was red or blue, into an acidic solution, then what you would end up with is the paper would turn red regardless. Okay, so red litmus paper goes into acid, stays red. Blue litmus paper goes into acid, it will turn red. Blue, however, will always represent a base. So for example, if I were to take this red litmus paper and put it into a solution of a base, then it would turn blue. If I were to take a blue litmus paper and put it into a solution of a base, it would remain blue. So I just remember the B and the B from blue and base, and that just reminds me that litmus paper, regardless of its original color, will be blue in a basic solution, and red will always represent an acidic solution, whether it began as red or it turned red once the blue was dipped into it. So here's a nice summary for you to see a little bit more, to explain a little bit more about what I just discussed with you. So red litmus paper in acid, you won't see any change, but if you test it with a base, it will go from being red to turning blue, and the opposite is true of our blue litmus paper. So phenolphthalein is another chemical, and I'll show you this in class as well. It's kind of cool. Basically, it's a chemical that if you add it to an acid, the acid would originally be clear and colorless, and you would add it to it and it would remain the same. But as soon as you added it to a base, then it turns sort of this beautiful pink color. And so we can use it to help us identify whether something is alkaline or acidic, because we know that in the alkaline solution it will turn this nice pink color. And if there's not enough hydroxide particles there, ions there, then it won't be basic enough, and so it will remain colorless. Okay, so the last item on our list today is to talk about something called the pH scale. And so pH is a term that you've probably heard in your everyday life, but really didn't have any idea at all what it means. So sometimes, consumer products will be listed as pH balanced, or I think about shampoo, for instance. Often they'll say it's pH balanced, or something to that effect, or something might be described as having a high or a low pH. So let me explain what the pH scale is and what it's meant to do. So the pH scale is a scale that's meant to give you some qualitative information and quantitative information about how acidic or basic or alkaline a substance is. Most of us are familiar with percentages, right? So if I say, I scored a 90% on a test, right away we know what that means. We can interpret what that means. And the same is true for the pH scale once you're familiar with it. So if I were to say to you, a substance has a pH of 2, well, that should give you some information about what type of material that you're dealing with. So the pH scale ranges from 0 all the way up to 14. And so anything that is below 7 on the pH scale is considered to be acidic. And anything that has a pH above 7 is considered to be alkaline or basic. And so right in the middle at 7, anything with a pH of 7 is considered to be a neutral substance. So as you may expect, pure water should have a pH of 7. Because it's neither an acid nor a base. And so if I were comparing something, let's say a material with a pH of 5 versus a material with something with a pH of 2, the substance with the pH of 2 would be much more acidic, because of course the lower I go on the pH scale, the more acidic the substance is. And conversely, if I look at the alkaline end of the scale, Drano, for instance, would have a pH of about 14, and it's far more alkaline than, let's say, Windex, which should have a pH somewhere in the 9 to 10 range. So as I go higher up on the list, materials are described as more alkaline. As I go lower on the list, anything with a very low pH is considered to be quite acidic. So just to add some more descriptors here, anything with a pH of 0 is going to be a very strong acid. And so what that means from a chemical perspective is that lots and lots of hydrogen H+ ions were dissociated and placed in solution. There's lots of them present in solution. So only a very, very strong acid would have enough H+ ions to reduce the pH down to 0, because it would be releasing so many of them. Now, conversely, any material with a pH of 14 would be considered to be a very, very strong base. Why? Because presumably its chemical structure is such that it releases a whole lot of hydroxide ions into solution. Now, what does it mean to have a pH of 7? A pH of 7 means that the substance is neutral, as we've discussed, but the reason that it's neutral is because that substance would contain an equal amount of hydrogen ions and hydroxide ions, and so that creates that neutral substance. So let me explain a little bit more. You'll remember in class the other day, we looked at, well, what happens if you have an H+ crossed with an OH-, right? Well, we talked about how that really would give us an HOH. But what is HOH? Well, I've got 2 hydrogens and 1 water. Oh, that's right. It's water. So water is the perfect example of a neutral substance. Now, although the litmus paper that we talked about earlier and the phenolphthalein, those indicators are great for telling us if a substance is an acid or a base, sometimes we want to know, well, how acidic or how alkaline is the substance, right? And so in that case, the litmus paper and the phenolphthalein, they just don't cut it. And so in that case, we may want to use something called universal indicator. And a universal indicator is just a liquid solution, and I'll show that to you in class, that depending on the acidity of the solution, when it's added to that solution will change a different color. And based on the color, we can kind of separate it into particular pH values. So for example, here we have something that is acidic, and I know based on my experience that anything that has sort of this orangey red color on using universal indicator will be more of an acid, a really strong acid. And then anything at the other end of it where I start to see purple solutions, that indicates to me that the substance is a really strong base. Now another thing, and this is where some of you with pools may recognize it's the pH paper. And so this paper here, I take a little snippet of it and I would dip it into the solution that I'm looking to determine the pH of. And based on the color of that little paper afterwards, I can classify the pH by matching it up to my little legend here on the pH paper. Now it's still, I'm still only classifying these as, pH of 1, 2, 3, and so on. But if I wanted to be even more precise, even to decimal places, then I can use something called a pH meter. And so the pH meter is just a digital device that has a little electrode on the bottom, and it measures electrical conductivity to a certain extent, and that helps for me to identify the pH of the solution. So those are 3 different tools that can help me to identify how acidic or how alkaline a solution is. Please look on Google Classroom for some homework questions that will be associated with this note, and please be prepared to answer some questions tomorrow in class.